Hi, my name is Shreya, and this is my Physics 2212 Lab 4 on magnetic dipoles and bar magnets. So I guess before we start, let's go into a little bit of a lab intro and the purpose of this lab. And so this lab was basically to understand the relationship between magnetic fields and the distance, specifically with bar magnets, which acts like a magnetic dipole essentially. And we did this both experimentally and using a computational model. And so here are some of the equations that we used. We used basically uh, the magnetic field formulas, the Biot-Savart laws, and also some of the distance and magnetic field relationships as shown right here. And we'll go a little bit more into this as we continue talking about the computational model we built with code and then also how we determine some of the values in the experiment. So the process of this lab was pretty cool. We started, well, basically we explored the relationship between distance and magnetic field, and that was the point, right? Um, and we did this by first placing a bar magnet at the end of a meter stick that we oriented based on the Earth's magnetic north. And we basically made this setup, this is part one, we made this setup perpendicular to the Earth's magnetic north so that we wouldn't have to consider the magnetic field due to Earth, and we can just simply isolate the bar magnet's magnetic field. And so for this first part of the experiment, we basically did this in 1D and we measured the different distances using our phone as a magnetometer and an app that we used. And we were able to, for each distance, we were able to calculate the magnetic field at that distance and then record the distances at which certain magnetic fields occurred and plotted them to see basically a correlation that we'll go over a little bit later. And then in the second experiment, this was kind of a 2D representation. So in this one, we had to also understand how the Earth's magnetic field might affect our readings with the magnetometer. And what we did here is we chose a distance d, and we went at a 45-degree angle and tried to calculate the magnetic field at that distance and angle. So this is our experimental data for part one, where we were just calculating the linear x distances and magnetic fields. So we had basically, we wanted to calculate the distances for each magnetic field, like 20, um, 70, 120, 170, and 220. And when we plotted it, we found this correlation here. And we basically found that like the larger the distance, the lower the magnetic field value. So we found that kind of correlation. And we also took these averages as well. And so we've got this equation, which we will use when we calculate um, n basically, because n is just the slope of this relationship. And then this part here is the ln of k. And we can take e to the power of negative 21.714 to get k itself. And then for part two, we basically we used dperp. We took three trials of everything. And for each dperp, we found the X, Y, and Z components of the magnetic fields. For Y, we also subtracted the magnetic field of the Earth so that we isolated the system being just a magnet. And then we have the net magnetic field averages here. So we calculated essentially the magnetic moment. And to do this, we found K using that first equation in part one. And we also found N, which was the slope again. And we used that relationship equation that I talked about earlier to get 1.8 times 10 to the negative 3 for the magnetic moment of the magnet. And then I ran through some code to simulate part two, which is a 45-degree angle one. And I initialized some things. This is like the magnetic field equation. We created a function for that, and then I put in the distance from my x from the experiment, and then I also put in my dperp from the experiment as well. Here I basically created arrows for on-axis field arrows and then also perpendicular field arrows. I created a bunch of different arrows for these. Four for perpendicular and two for on-axis. And here's the result of my simulation. I got some on-axis arrows that match with the dipoles, or the effect of the dipole, but magnetic field. And then these are the off axis and perpendicular ones as well. So sources of error are other magnetic fields present, so phones and computers. We also have the lack of precision in measurements using the ruler because we were eyeballing things, and we also didn't know the exact location on the phone of the magnetometer. We also could have failed to properly align and calibrate the magnetometer. Additionally, for what ifs, if we hadn't oriented our experiment to compensate for the magnetic north and just laid out on a random angle, the magnetic field of the Earth would have definitely been on X, Y, and Z components affected. The readings on our magnetometer. So relating distance and isolating the magnetic field of just the magnet would have been difficult. And if we had stuck two identical magnets together end to end and done it again, we would have just gotten a larger magnetic field magnitude, but the directions would have been the same on axis and off axis. Thank you.